Good afternoon. We welcome you to the cultural event that the Princesa de Asturias Foundation has organized as a tribute to the recipients of the Princesa de Asturias Award for Scientific and Technical Research 2020. The event, Invisible Mathematics, is part of a cultural program with which the foundation aims to bring the work of the winners closer to the general public, and that takes place on days prior to the ceremony hour. The circumstances imposed by the COVID-19 pandemic have not allowed us to have all the winners in Asturias, as it was our wish, but in this digital format, it's an honor for me to have the 4 winners in the category of scientific and technical research gathered in this set. Just for the public, imagine that I know you are a soccer fan and suddenly someone asks you to present a debate with Messi, Ronaldo, Iniesta, and Joaquin. I'm sorry, but I am very supported. That's exactly my situation today. I love maths, and I am an absolute fan of the 4 stars we have here, and I'm so nervous and so excited. So we welcome Professors Ingrid Daubechies, Yves Meyer, Terence and Emmanuel Candès. It's a pleasure to have all of you with us. And the structure of this event is as follows. Firstly, its professor will make a brief presentation of their work, and then they will talk briefly about the impact of mathematics in different fields, impact that sometimes, many times, it's unknown for the general public. So it's an honor for me to introduce you, the Professor Emeritus at École Normale Supérieure de Cachan, Yves Meyer, who, among a lot of things, was awarded with the Abel Prize in 2017. So, Professor Meyer, it's your turn. Thank you.
Thank you very much for this presentation. And I would like to talk about the relevance of wavelets in a major discovery of the century, which is the detection of gravitational waves. So the gravitational waves have been predicted by Einstein's theory of general relativity, and they are steadily sent to the Earth. And here is a picture of Albert Einstein. And the first detection occurred 5 years ago, before such signals could not be detected. But 5 years ago, everything changed, and we had the 4th of September, we had a first detection. So I will talk about this detection. So this first detection is a spectacular discovery. The gravitational waves were produced during the final fraction of a second of the merger of 2 black holes to produce a single, more massive spinning black hole. So the collision of 2 black holes had been predicted but never observed. So the man who designed the algorithm for detecting gravitational waves is Sergei Klimenko. Now he is speaking. So about his research program, I developed a search algorithm named coherent wave burst. on September 4th, 5 years ago, the coherent wave burst algorithm discovered a signal from two colliding black holes 3 minutes after the data was collected from the LIGO instruments. So it is a very, very rapid algorithm, very efficient. The key feature of coherent wave bursts are that by using wavelets, it explores the time frequency structure of the data. So here is the reference. So here is a picture of Sergei Klimenko, and I am on the left. Klimenko's algorithm relies on an achievement by Ingrid Daubechies, Stéphane Jaffar, and Jean-Yves Journet. Daubechies, Jaffar, and Journet were motivated by Kenneth Wilson's work. Kenneth Wilson was awarded the Nobel Prize in Physics for his work on critical phenomena using the renormalization group. Here is a picture of Kenneth Wilson. So it is a collaboration between mathematical signal processing and physics that allow to construct this algorithm which detected gravitational waves. So what are time frequency wavelets? Wavelet analysis was launched in the late 70s by a visionary engineer, Jean Morlet, and a marvelous physicist, Alexander Grossman. Ingrid Daubechies joined the team, and I happened to be the fourth musketeer. Wavelet analysis became compressed sensing through the achievements of Emmanuel Candès and Terence. Wavelet analysis became deep neural networks in the hands of Stefan Malloy. Since 6 years, I am collaborating with Alexander Olewski on a completely distinct subjects on mathematical problems around quasicrystals. Let us rejoice and be glad. Thank you very much.
Okay, thank you, Professor Meyer. Thank you very much. As now is the turn of the James B. Duke Professor at Duke University, Ingrid Daubechies. Thank you very much for being here with us today. Professor Daubechies is very known, but for her work in image processing. So it's your turn, Professor Daubechies.
Well, thank you. Because I had seen a glimpse of the presentations of my co-recipients, with whom I'm so glad to be part of this award, I thought that I would provide a light counterpoint to all the scientific work and medical work and so on, beautiful work in which it's been my privilege to be involved as well. And I tell you a little bit about applications of time frequency and time scale analysis and wavelets and other techniques to a completely different field in which I have been working for the last 10 years or so, which is the use of these techniques to help art conservators and art historians analyze paintings in the collections of great museums and get other insights in those. So let me share my screen. Okay, so, oops, I don't know what happened here. Okay, so let me tell you about one particular project in which I was involved, which is an altarpiece by a not very, very famous painter at all, a 14th century Italian altarpiece, of which many different panels are in different museums in the United States. And it was only recently, well, a few decades ago, it was realized that they belonged originally to the same altarpiece, and an exhibition was planned to bring them all together. Now, one here was missing, and they decided to commission an expert on ancient painting techniques to make one using all the original techniques of the 14th century, which would then give a panel that would be beautiful and new and show to the viewers of the exhibition what these panels looked like when they were brand new. I mean, with vibrant colors and gleaming gilding behind it. And then they realized they couldn't put it next to the old panels. Here you see what actually was shown on the exhibit. And in order to not shock the viewers, they actually made an aged version. Well, we made an aged version of the original painting. And we showed it. That was then printed out and put together with the others. And let me see whether I can show you. I mean, whether can I bring this up? No, I don't think so. I don't know why not. Oh, here I have a website. I think you will have to cut some of this stuff. I wanted to show you how we aged that one painting. So this is what I'm showing now. So this is the new painting, and we had to do lots of aging of the colors and bringing in cracks and so on. And here you see the transformation that we managed to do with image analysis and time scale techniques and wavelets in order to do that. Now, once we could do that, we could, of course, also rejuvenate the old panels. Here you see one of those old panels, and let me show you its rejuvenation. I mean, how the colors become more vibrant. And in fact, we did that for the whole painting. So here was the old painting in its full glory with the aged printout. Here is what we virtually reconstructed, is as close as possible as we can without inventing anything to what it must have looked like new. Now, in the study of all that, we looked at various different views of those paintings. And here, for instance, is an enlargement, a detail of one of the old panels. And we looked at the X-rays. And that seemed like very, very peculiar. All this trellis of stuff behind it. So that is caused by what's called cradling. These panels typically have been thinned very much by conservators in the 19th and early 20th century, which means that they make the planks much thinner and then put a lattice work on the back in order to give it physical integrity. And that, of course, when you look at X-rays, gives you the cradling behind it very visible on the painting. Here's another painting that has that cradling. Using wavelets and other techniques, we did built image analysis tools that allow us to remove that cradling, and not just the cradling, but also the wood grain of the cradling, but leave the original wood grain and painting intact. So it makes it possible for art historians to look much more closely at X-rays that were very difficult to share before. Actually, when I first saw this whole application, and I asked, well, it would be useful for our GISI project, but was it worth developing a whole tool? I talked with people, and the head of imaging at the Prado told me, I asked, do you have this problem too? She says, do I have this problem? And she showed me many and so on. And that's when we developed this tool. So you see, the image processing is wonderful for science, for medicine, for physics, and for art conservation. And that's what I wanted to say.
Thank you very much, Professor Daubechies. Thank you. And now let me tell you something personal. You can try to look for one of my personal pictures on Google. In that picture, we can see an old man and a boy. The old man was Paul Erdos, and the boy is not a boy anymore, but I'm sorry, but it's the truth, that one of the leading mathematicians in the world is Professor Terence. Is your time.
Thank you very much. Yes, I'm very happy to be here virtually. It's a shame I couldn't be here in person. Yeah, so this prize is a prize recognizing applied mathematics, and I am not an applied mathematician. I work in very pure areas of mathematics. But the amazing thing about mathematics, it's all connected, pure, applied, it's all unified. And I want to give you sort of a story. So this work that I was involved in, compressed sensing, is applied, but it is connected to areas of pure mathematics. And even to very simple and very classical questions in pure mathematics, such as coin weighing. This is not exactly how I got involved in this, but it makes for a good story anyway. So I wanted to show you how even very pure topics are connected to applications. So this is a very old puzzle, over 100 years old in mathematics. It's the 12 coins puzzle. You're given 12 coins. And 11 of them are exactly the same, they're identical. But one of them is counterfeit. It is either heavier or lighter than the other 11 coins, but you don't know which one. And you're supposed to work out which one is counterfeit. And the only tool you have is a balance scale that you can put some coins on one half of the scale and some coins on the other half and weigh them and see which one's heavier, which one's lighter. And you're only allowed to use the scale 3 times. And the question is, using only 3 measurements, can you decide which of the 12 coins is the heaviest? So this seems like the answer should be no. Normally, when you have 12 unknowns and only 3 equations, this is what mathematicians call an underdetermined system. And usually we can't solve the problem. But in this case, the answer is yes. With only 3 weighings, we can work out which of the 12 coins is the counterfeit, and even whether it's heavier or lighter. And the reason you can do it is because our data, the coins, has a special property. It is sparse. If you take all the weights of the coins and you subtract off the weight that it should be, most of the coins have 0 weight after normalization, and only 1 coin has a non-zero weight. So and in mathematics, we see that the data, the signal that we're trying to understand is sparse. And what we've learned in the last few years is that because you're sparse, you can collect data much more efficiently. Now, there are many ways to solve this problem, but for the purposes of leading to compressed sensing, the most relevant way to do it is through a matrix. So you design a weighing matrix. Okay, so you have 3 weighings, weighing 12 coins, and you can describe a weighing procedure using a matrix. So here we have a matrix with 3 rows and 12 columns. And this matrix is designed so that every row has got 4 ones and 4 minus ones in it. And the 4 ones are the positions of the coins that you put on the left of the scale. And the minus ones represent the coins that you put on the right of the scale. So for example, the first weighing, which is the first row, you would put on the left-hand side, the first coin, I think the 7th coin, the 9th coin, and also the 6th coin. And then the coins correspond to the minus ones you put on the right-hand side, and you weigh those coins against each other, and that's your first weighing, and then this is the recipe for the second weighing, and this is the recipe for the third weighing. Now, why this particular weighing matrix? Well, so once you do a weighing, so for example, suppose the 4th coin is counterfeit and is light, then you can actually work out the outcome of your weighings by matrix multiplication. So this is your data. You have 11 coins that are 0 weight once you normalize, and 1 coin that's light. So I put a -1 here, and you can multiply this vector by this matrix. That just gives you the negative of the 4th row, which, if you look back, is actually 0, -1, and 1. And what that tells you is that the first weighing will be balanced, and the second weighing will tilt to the right, and the third weighing will tilt to the left. So this is the measurement that you get out of this data. It's a lot smaller, so it looks like you're losing a lot of data. But the key property that makes this work is that I chose this matrix. It has a special property that all the rows are independent. Any two pairs, any two columns, are independent of each other. That no column is a multiple of any other column. And because of that, every coin has a different signature. And so each coin gives you a different measurement, and the heavy coins and light coins also give you different measurements. And so you can read off from the matrix and from the measurement what the coin is. And so the key property was that the columns were somehow very different from each other. In this case, different means independent. And it turns out that this is part of a more general phenomenon, and this was realized a lot later. And this is now what is sort of the foundation of compressed sensing, that if you want to solve a system of equations, linear equations, AX equals B is what we call them in mathematics, and if they're underdetermined, so that the number of measurements we have, which I'm calling little n, is a lot smaller than the amount of data you have, which is capital N, you can still reconstruct the signal if you know that your data is sparse, so not too many non-zero entries, and the matrix has to have a special property. So, for example, it should be what's called incoherent, that a certain number of columns should be independent, as linearly independent as a bare minimum. Actually, nowadays we actually ask for a stronger property, which is more technical, and but you actually ask for any set of columns to be almost look like an isometry. They should preserve distance. And so this has led to a very important property in compressed sensing called the restricted isometry property, which unfortunately has the acronym RIP, which in English means rest in peace, but still the name has stuck. So there's this metric property called the RIP that some matrices have. And if you have it, it turns out that you can work out you can solve these equations AX equals B. And furthermore, you can actually solve them quite quickly. There are very fast algorithms to solve them. Again, maybe this is a bit too technical, but this is one of the algorithms that we use to solve AX equals B now. If you know X is sparse, there are many solutions because it's underdetermined, but out of all the solutions to this equation, if you pick the one that minimizes what's called the L1 norm, which is the sum of absolute values of the coefficients, then we can, in many cases, we can guarantee that you actually get a nice sparse solution, which is often the solution that you actually want. And then finally, the final ingredient that makes this theory very effective is that, in fact, many matrices obey this RIP. So this is more the work that I got involved in, that you can use tools from an area of pure mathematics called random matrix theory. And they showed that many matrices of various types, especially random matrices, actually obey this RIP, and therefore all these nice properties work, and compressed sensing becomes possible. And then actually Emmanuel will show in his next presentation actually how this is applied in medical imaging, for instance. There are still theoretical questions left. I said that random matrices obey this RIP. There's actually still an open question whether you can construct non-random matrices that obey this property. That's a question I'm still interested in, but that's more a theoretical question, not one for applications. Okay, that is all I have. So thank you very much.
Okay, thank you very much, Professor Terence Tao. And finally, last but not least, it's an honor to introduce the man who found a method to solve a very, very, very hard problem, just playing with a ghost. Is the Barnett-Simons Chair in Mathematics and Statistics at Stanford University, and is Professor Emmanuel Candès. Bonjour, it's your turn.
First, let me say gracias to Foundation Asturias for this tremendous honor. I'm very delighted to share this with 3 co-laureates that I really admire. So to put my work in context, let's look at magnetic resonance imaging, a wonderful modality that lets you image body tissues. And doctors here would like, of course, love to see an image as that on the left, but that's not what an MR scan sees. That's not what a magnetic resonance scan sees. What the scan sees is what you see on the right over here. And this is, of course, very different. However, and this is perhaps our first example of the power of mathematics, it is possible to recover the image on the left from the data on the right by solving a linear system of equations. The unknown here are in the system are the pixel intensities of the left image. Now, doctors, for reasons you understand, want high resolution images so that they can see fine details and they can see, for example, where a duct has been occluded or not. And high resolution means lots of unknowns, lots of unknown pixel intensities. Now, we've all been to high school, and what we've learned is that I need as many equations or equivalently as many data samples as unknowns if I want to solve my system of equations. And that's a real problem because magnetic resonance data collection is inherently slow. You can imagine having a clock ticking each time you get a new data sample. So it goes something like this, tick, 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 and you get the idea. And before you actually get a complete scan, it takes a really long time. People stay a long time in a scan. And that's really a problem for children. If you imagine putting a children in a scan, for example, a 2-year-old, for a long time, she will move. She will move because she cannot stay still or because she cannot hold her breath for very long. And so just as in photography, when you move, you have what's called motion blur. And so what this will do, it will produce medical images that are unsuitable for diagnostics. Now there are solutions to this, but the solutions are a bit scary. For example, if you want to eliminate motion, what you can do is you can stop respiration in the child for something like 2 minutes. But you can imagine that if you stop respiration, if you deprive the brain from oxygen for such a long time, your abdomen maybe is the least of your worries. So we need to go faster, and going faster means collecting fewer data samples. And as we've seen in high school again, we know that it's going to be a problem when it comes to solving linear system of equations that do not have sufficiently many equations. How are we going to do this? But what if I were to tell you that what you're looking for is sparse, which means that the solution you're looking for has lots of zeros. You don't know where these zeros are a priori, but you know there are quite many zeros and only a few non-zeros scattered here and there. Now I'm going to take this abstraction. I'm going to connect this to medical imaging in a second, but let's take this abstraction for a second. Suppose that someone tells you that you have lots of zeros in your solution. Then it makes the search for solutions feasible. And so what now we're going to do mathematically is we're going to say, okay, we don't have many equations, so there are potentially many solutions, but we're going to try to find the one with as many zeros as possible. The way this is done is by solving an optimization problem, a tractable optimization problem, where we're going to try to find a solution Z that has as many zeros as possible and match the data samples you gave me. And so the way we do this is by minimizing the sum of the pixel intensities of the image you're looking for, subject to data constraints. Now, this is extremely tractable, and we can run this algorithm very quickly on modern computers. And the surprise is something like this, which is under conditions on the sensing matrix A and the sparsity of your solution, this optimization problem delivers a ground truth, very surprisingly, still, in my opinion. That is that this mathematical optimization spits out exactly what you're looking for. And so what this says abstractly is that you can solve underdetermined systems of equations, even though, and that's almost, it's a bit of a miracle, even though you're missing most of these equations. All right, so we know that images are not sparse. What does it mean to be sparse? It means that a lot of entries are zeros, and we can see when we take photographs that a sparse image would be nearly black, where almost all pixels are zeros, but that's not what reality is. But thanks to the wonderful work of Yves Meyer, Ingrid Daubechies, who developed wavelets, if I look at these images through the right prism, through the wavelet transform, for example, they become sparse. And that's what the theory uses. So we're in business, and thanks to absolutely extraordinary researchers in medical imaging, and you see their names in blue, we can now apply these mathematical techniques to get exquisite scans of children. And so what you see on the right here is a scan of a 6-year-old, which has been accelerated 8-fold. So instead of taking 2 minutes to acquire, it takes 16 seconds and still has all the resolutions that doctor needs to issue a medical diagnostics. And so from the mathematical consumption to the realization has, of course, taken a lot of work from a lot of people. And with this, I would like to thank you for your attention.
Thank you very much, Professor Candès. Merci beaucoup. And thanks to the four of you. And now you can talk freely about the impact of math in other areas. But let me ask you a question, because I'm very involved in maths popularization. And we would like to know your opinion into related questions. One is, do you think that the general public, in the society in general, knows the fundamental role of mathematics in many of the aspects of everyone's lives? And second, what do you think can be done in order to show the importance of the mathematics and the beauty to society?
Well, I think many kids get a lot of mathematics in school and are told all the time that mathematics is very important, but don't really, on the one hand, get an impression of how professional mathematicians experience mathematics as a very alive and very creative and very changing subject. That's very exciting. I mean, it's very living. It's not lots of formulas on that pages. On the other hand, don't really get insight in those connections that do exist. All the mathematics plays such a big role in so many aspects of daily life where it's hidden. I mean, so I think we have, and you have, a job to do in helping in the outreach of mathematics. And I think we also should do a better job in teaching mathematics in schools.
Anyone else?
I'll say something. Yes, I think there's a real disconnect. I mean, when we study mathematics in schools, we use one part of our brain, very analytical, formal part of our brain. And when we interact in real life, we use a very different part of our brain, using analogies and real world intuition. And for many people, they never make the connection. And so math is somehow separate from everything else. Like, there are kids who can't tell whether 2/3 is less than 3/4 or not. But if they're given a pizza and they either cut it into thirds and they take two slices, which is bigger. And some people just never make the connection. Another example is that one of the most unintuitive things in formal mathematics is proof by contradiction. But people use proof by contradiction all the time when they argue in real life. In fact, even kids, there's a theorem that kids teach each other by proof by contradiction, and it's not taught by teachers, it's taught by other kids. The theorem is that there's no largest number, there's no largest natural number. And kids teach each other because they play these games in the schoolyard where they say, who can name the biggest number? And then someone names a really complicated big number, and the other person just says +1. Like, that number +1. I win. And this shows that there is no largest number. It's a perfectly good proof by contradiction, but people don't connect that with their formal education. So it's a tricky problem. I mean, I think with a good teacher, you can yes. Get teachers to make the connection between the formal side of mathematics and the real world, but it's not easy. You need a skilled teacher.
Maybe I'll say one thing a bit orthogonal to what has been said, which is I think kids and the public in general needs heroes. And in the mathematical world, we're not very good at producing heroes. Physicists are very good. Meyer showed the picture of Einstein, and everybody knows Einstein, and everybody knows about Isaac Newton. But their mathematicians, in my view, are as giant as Newton and Einstein. For example, Claude Shannon. Claude Shannon is a mathematician who laid out the foundation of communications. Without Claude Shannon, it's not an understatement that we would not be able to communicate the way we communicate today. Without Alan Turing, we might not be able to compute the way we compute today. And so I think as the community, we need to do a better job at, and I hate if I sound a bit crassy, but we need to do a better job at producing heroes. And I think that's an important thing to do. Unfortunately, the kind of heroes we see sometimes in Hollywood movies are not exactly what the public expect. You know, these are usually portrayed as weird mathematicians. Claude Shannon was not weird at all. And so I think we need to educate the public about our heroes and what they've contributed. So the digital society, the digital age we live in. You know, Einstein did a lot of important things, but I would argue that we live in the digital age, not in the age of relativity. And I think we need to celebrate this a bit more and create heroes.
Professor Meyer, are you agree?
Yes, yes, it is a very important, interesting question, but I would not separate mathematics from physics. My great event in my life has been to meet and almost fall in love with Alexander Grossman, who was a theoretical physicist. And for Alexander Grossman, there were no boundaries between physics, mathematics, and signal processing. And for me, it was a true discovery. The fact that these fields could be unified was, and I got that when I was 44, and before I thought that mathematics were a separated world. But when I understood the connection, the deep connection with physics and signal processing, I was absolutely in the heavens. It was absolutely remarkable. And I owe that to Alexander Grossman. And he was in our Wavelet group, he was truly the conductor of the group. And we were the performers, Ingrid and I, and all the other were just performers. And we need this type of conductors in the science. So I wouldn't separate mathematics from science. I think, and the message to the kids should be like that, not arguing against physicists, the way they teach and the way we teach, and that we do not have a common language. We do have a common language. Thank you very much for asking this question.
Yeah, we have a common language, but because in mathematics, we like to really take apart what makes a reasoning exactly work. We like to put our finger on what exactly makes it work and so on. So we can sometimes drive that a bit too far. And that's what people then remember of mathematicians, that we are the people who like to cut hairs in four to see how many people, and I think we need to be better at not bringing that aspect out completely, and at showing how alive it is and how connected it is to everything. I mean, I know there's this famous saying about the unreasonable effectiveness of mathematics. Okay, I don't agree with that at all. I mean, unreasonably effective compared with what? For all those things that you want to use it for, you only have math. I mean, it's what we have. Math is the name we give to our way of thinking about what we observe and and so on. And we like to see patterns, and then we like to do pure math as well, because we are good at that. We are good at seeing patterns and analyzing them and having pleasure in thinking, but that's what we have. And so it is all connected, and it's all, yeah, sorry.
I agree with both Yves and Ingrid. I'm going to embarrass Ingrid a little bit by telling a story, because Ingrid was my math professor when I was a graduate student at Princeton. And yeah, she taught a signal processing course that I was in. And at one point you were discussing convolution. And I'd already known about convolution from my harmonic analysis classes as a very formal concept, but you kept referring to convolution as blurring. He says, I'm going to blur this function by a Gaussian. And it never occurred to me, and I think you actually used the metaphor of taking off your glasses to look at something. And it never occurred to me that this mathematical operation, which I'd only understood formally, was actually literally connected to something I could see. I mean, I can take off my own glasses, and it really opened up. It was a revelation for me that these sort of very formal operations were actually very physically intuitive concepts. So yeah, it is very important to always keep tying abstract mathematics to the real world.
Mm-hmm.
Thank you. A personal question. Do you have, all of you, a problem that you bring to solve, something like the Riemann hypothesis or something similar?
Well, I don't. People sometimes ask me what my favorite problem is, and my favorite problem is the one I'm working on right then. I mean, that's the one I'm most obsessed by, and it's like so. And the favorite thing I learn about, well, I like understanding what happens. So when something big happens, in mathematics, it's fun to try to understand it and to. But I personally have not been motivated by trying to understand. I mean, I never wanted to go into doing things like the Riemann hypothesis or well, Navier-Stokes maybe a little bit more, but I'm not a PDE person so much. But but I should let the others speak.
Yeah, so I'm in the same camp. I work in applied mathematics and statistics, and my work is not motivated by open conjectures in pure mathematics. Rather, what we do, I think, is we see the world around us, and we can try to understand how mathematics can contribute to the world around us. Since I've been working on recently, and you'll see how far I am from the Riemann hypothesis, is the fact, for example, that people now use machine learning, AI, to make important decisions on our behalf. For example, you can think that in the United States, courts are actually using AI algorithms to inform decisions about who should get paroled and who should get bail. And so one important question here is, how do we make sure that these algorithms are not discriminating against people? How do we make sure that it between quotes fair? And so there's a lot of opportunity for people, mathematicians, statisticians, and applied mathematicians like myself to contribute. And so I think, as far as I know, as I'm concerned, my work has always been more trying to draw bridges between a form of abstract reasoning and a real world that I can see. And so, yeah, maybe I should let others speak as well.
Professor Tao, Professor Meyer.
I'll say something. I think there's a popular mental model that people have of mathematicians, which is wrong. So the model is that every mathematician has some sort of talent, like some intelligence, which is some number, IQ or something. And then problems also have some difficulty level. And the mental model is that as long as your intelligence is greater than the difficulty of your problem, then you can solve the problem. So the smarter you are, the more problems you can solve. And the main factor in whether a problem is solved or not is whether the person trying the problem is smart enough. And that's not really true, actually. I think mathematics is more like fishing. That there are good fishermen and there's bad fishermen. But even the best fisherman can't just sort of automatically get a fish whenever he or she wants. You have to be in the right place. You have to be in a place which is promising, where there are already lots of fish you can see. But you still need luck, and you need also to build upon what has been done before. Most of what we do is built upon previous breakthroughs. So there's lots of problems which I would love to solve. Okay, Riemann hypothesis, of course, I would love to solve it. My personal favorite is something called the twin prime conjecture. But I don't have a chance. I mean, well, okay, I do admit maybe once or twice a year I try privately and fail. But it's often a matter of opportunity, and you have to. The time has to be right, and you have to recognize other breakthroughs and build upon them. It's not really just a matter of being smart enough. Sometimes problems are ripe to be solved, and then any reasonable mathematician in the area can have a chance. But then some are just not ready. Like the Riemann hypothesis, we are not ready to solve for decades, I think, still. But you never know. There are always surprises.
Professor Meyer?
Yes, very good question. Very recently, I have been working on some problem who was very close from the Riemann hypothesis. Let me be quite modest and speak about the work of André Guinan. André Guinan was an Australian mathematician who worked in Great Britain under the direction of Hardy and Littlewood, and he spent all his life on the Riemann hypothesis. And he wrote a paper in Acta Mathematica 60 years ago with a lot of claims, but without any proofs. And I was fascinated by this paper, and I proved the claims of Guinan, and that gave me a very intense pleasure. There is a tradition in mathematics and in heritage. So we inherit from older people, and we can continue their dreams, It is a dream of the humanity that never stops. It is like a river, It is a river which continues forever, and that's beautiful, the tradition in mathematics. I love that. I love that not because I am a traditionalist, but by respect of these people, of their love, and it is a continued love.
Thank you very much. So we have time, I think, that for the last question. I would like to know what do you think about this? It's fair to talk about pure and applied mathematics, or just talk about mathematics?
Well, I very much, and I think others have said it, I believe you just think it's mathematics. Actually, I have done work that's more pure and more applied, and it feels exactly the same from the inside. I mean, it's not that you say, oh, today I feel more like an applied problem, or today I want to do a pure problem because I'm in a pure mood. You want to understand, and you want to build understanding and then use that understanding. And so the impetus, the feeling as you do it is the same. The difference is what you connect to. But even in pure mathematics, people connect to other branches of mathematics. That's usually the most exciting discoveries. The ones that people are really excited about is when people use techniques that have matured and that are well developed from one branch, and they all of a sudden can use it to solve a problem in a different branch of mathematics. And people are excited. And that, if you want, is like an application, but within mathematics. And so I think the taste of individual mathematicians on what they like to think about can differ, and you have an enormous spectrum and there's no precise line. But what we do when we work on it, it's all mathematics.
Anyone else?
I'll say something. It's funny how perspectives on mathematics have changed over the centuries. So, say 100, 200 years ago, math was just part of science. People like Newton or any of the great scientists of the past, or mathematicians, they did math and they did science. Poincaré, everyone was sort of both. And then maybe 100 years ago, it started splitting up, and then math became these sort of silos of different fields. Some people just worked on the algebra silo, some people worked on fluids silo or whatever. And then it became like a pipeline. People, maybe the idea was that you started with the basic sciences, like pure mathematics, and then that fed into applied math, and then into engineering and technology and so forth. But I think the more modern viewpoint, I think it's really an ecosystem. It's not just a food chain; it's a food web. Right? Every field connects to every other field. So pure mathematicians sometimes solve problems that applied mathematicians can use, but conversely, applied mathematics can generate interesting questions and insights that feed back to pure mathematics. And it's the same relationship between mathematics and physics, between mathematics and information science, economics. It's all a web, and you need people at every single node of this web to have a healthy, thriving intellectual environment. No one is important. There's no keystone which is more important than the other. But but the whole is much bigger than the sum of its parts.
Mm-hmm.
So, Candès, Meyer, something to add?
I agree with the previous comments about the unity of mathematics, of course, and also about the notion that we need a web. And that's what we try to promote, and I think it's extremely important. To speak to your question about the difference between applied mathematics and mathematics, of course, it's different faces of the same coin. And so still, I think that it's where do you get your inspiration from, right? So if you work more on the applied side, you're going to pay tremendous attention to what's happening in fields surrounding mathematics, in the sciences, in engineering. And so you're going to try to understand how you can contribute to these fields. And so I would say that when you work in applied mathematics, you get your inspiration from a different place, and the end of your work may not be mathematics itself. And that's a bit different from perhaps if you work in number theory, for example, where perhaps your inspiration does not come from field around you. But I totally subscribe to Terence and Ingrid's point of view. There's just one, and it's called math, and we need a web. And if we start to remove parts, things will start, the fabric will start to tear apart. And so, yeah, that's what I have to say.
And Professor Candès, what do you think about?
Yes, I would mention a mathematician I admired very much, and who created applied mathematics in France. In France, we have a we had a tradition of pure mathematics, which was very strong, but applied mathematics were viewed as something negligible for a very long time. And Jacques-Louis Lyons proved by his life and his commitments that the interaction between pure and applied mathematics could be fruitful to both sides. And I admired very much Jacques-Louis Lyons, and I think a year where I had lost a very good friend, I was very depressed. Jacques-Louis Lyons asked me to solve a problem about vibration of space labs. He wanted to understand the type of vibration of space lab. And I was sure I could not solve this problem, but he convinced me. And a week after, I gave him a solution. And that for me was a true revelation. And it was just 1 year later, that I became a member of the fourth musketeer of the wavelet group. It means that from time to time there are gigantic mathematicians who, like Jacques Lyons or like von Neumann, who played this fundamental role because he invented the digital computer and he was a fabulous mathematician, who can just as easily contribute to pure and applied mathematics. So it is not a modern mood. It existed a long time ago. And even Alberto Calderon, Alberto Calderon was first an engineer and worked in a few years in engineering in Buenos Aires until he met Anthony Zygmunt, and then he moved to pure mathematics. But he was always sensitive to problems in applied mathematics, and he solved he was already old when he solved a problem, an inverse problem for conductivity of the Earth. And he's very famous for that. So there is a problem named Calderon problem, which is a problem of applied mathematics. So among those people, I would, of course, mention Ingrid Daubechies, and but there are some persons who forever have been unable to put a barrier, a boundary between pure and applied mathematics. And we can even think about Archimedes. Thank you very much for asking this question.
Okay, I'm really sorry. I'm enjoying. For me, this debate is like a dream, but it's real when we are here. I'm really sorry, but I think that it's time to say goodbye and to close this event. I don't know if you want to say some words to finish this out, or just we are closing.
So I would like to say a final word. I am so pleased that the prize was shared. I like sharing everything, sharing mathematics, and the idea that the prize was shared, and between us, people who are friends, and we were friends forever. So it is marvelous. There are I was very sad when I received the Abel Prize, because the Abel Prize should have been shared. Wavelets was a common enterprise, and it is obvious that, for example, Ingrid would have deserved the Abel Prize much better than I feel I've always felt that, Ingrid. So I am so happy that this injustice is corrected today.
Well,
I'm sharing with you. We
Well,
shared
thank
wavelets. We shared wavelets, and we have to share the prize.
I am. It was for me too a very great pleasure to see that the four of us were united in getting this prize. I mean, as this panel has shown, we are people who are different, have different, but very much agree on many things, and
Yes.
and enjoy knowing each other and
Yes.
and contributing, and I hope inspire others, young people.
So speaking of youth, Yves Meyer was my undergraduate teacher, and I think he played an enormous role in my life. I don't know that I would be a scientist today if I had not met Yves as an undergraduate, not knowing what he wanted to do with his life. There are two people who played an outsized role in my scientific upbringing. One is Yves Meyer, and the other is my PhD advisor, David Donahoe, and I wanted to say this. Ingrid, I've known her for a long time before I met her, because I was so in love with what Ingrid Yves was teaching us in college, that everywhere I would go on vacation, to sporting events, anything, I would take her books with me.
Oh my
And
God.
my
They're
wife,
full of typos.
and it took a while. And in fact, when I got married, my wife would say, Emmanuel, are we taking Ingrid with us on vacation?
Oh my. And oh well, I think there's nothing much I can say to that, except the book is full of typos.
Okay. Okay. Sorry. Sorry.
Oh. Okay. No, I want to say I also have a very well-worn copy of Daubechies' 10 Lectures on Wavelets in my office. Yeah, and yeah, no, it's great to see all my old friends again.
And maybe sometime we'll be back all together in Asturias.
Yeah, I really wish we could have been in person.
Yeah.
And it's also great that that Spain, I mean, recognizes, you know, just basic science. You know, I think it's important, especially these days, just to be reminded that it's still valued, and you know, and that, you know, it's not all, you know, politics and yelling at each other, and you know, we can still sort of celebrate just very, very simple things.
Okay. I'm sorry, but I think that it's time to close. Thanks to the four of my stars, my mathematical stars. It has been a very interesting event. I'm sure that the public will enjoy the presentations and the conversation as much as I enjoy them. And it's points left from my side to add anything. And so, but thank you, Professor Ingrid Daubechies, Professor Yves Meyer, I think that's the right, Professor Terence and Professor Emmanuel Candès. And thank you to all the public for his presence, that we feel in spite of the circumstance. See you in Oviedo next year, and may the math be with you.
Okay.
Okay. Muchas gracias.
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 Okay. Muchas gracias.